All right, community. This is Hyun Lim calling in from Seoul, Korea. He's the co-founder, CEO of UBFi, and he will be talking to us about their new battery system. What's this all about, Hyun? Can you please let us know?
A battery. Basically, this is one of the most important thing in the drones. So to introduce myself briefly, I'm the CEO of UBFi, and my GitHub ID is Hyun Lim, and I wrote some survey paper regarding some open sources, and our company is doing drone light show with this smart battery. So drones love this energy bar a lot. So do we use this energy bar in the right way? That's the key question today. Our old friends, LiPo alarm, you may use to it to prevent undervoltage problem. And LiPo balancer is solving the cell balancing problem. But do we really need this equipment? With smart battery, probably not. So the first electrical vehicle, and between the modern electrical vehicle, the main innovation, I think that is a BMS, battery management system. So everyone was on the same line in 2014. Even this famous consumer drone was using a battery without battery management system. Now all has been changed. What's been developed since 2014 and why? The first job of the smart battery is protection. So the protection is about knowing when it is danger, the short circuit, hot temperature warning. That's the main job of the protection. And prediction is know when it will be empty. That's very important. So the gauge indicator indicates the very state of charge in percentage. And precaution is know when to stop use. For example, as long as you are using the battery in 100 times, 200 times, it degrades. So it's important to know when we have to stop the use the battery. So cycle counter and remaining state of the charge is in charge of this. Even smartphone implemented this feature, a smart battery, in just in 2019. Why? So this is a user interface of iPhone, and you can check the maximum capacity of the battery, which is basically a state of health, which indicates when you should change the battery. Because it is complex electrochemical device. Even though it looks simple bar, that's pretty hard. So, but the most important question to this energy bar is, how do we know how much percentage of energy left? So you might use to this gauge and even this small patches in a consumer battery shows the desire of knowing percentage of energy left. So just by looking, you will see the same battery, but it has different level of energy. How do we know inside a battery? So basically, it's very hard to know because the one metaphor you can imagine is a gas tank of the car. How does your fuel gauge of the car know the level of fuel? Can you guess how much fuel inside this fuel tank? To figure out the fuel gauge, there are a lot of devices involved. Even this measuring simple oil level is complex. So measuring the battery is also very complex. So how can this achieved in the PX4? In the PX4, based on voltage and current measurement, there are simple estimator inside. So this estimator estimates the remaining capacity based on internal resistance of the battery given by a user, and also the battery voltage and the current consumption. However, this is not working 100% always. For example, someone get 100% level still, even the accumulated consumption is this much. Why is it not accurate? That's let me answer to this question in a few ways. First, you can imagine a battery in this diagram. So even though the battery model itself is a simple, there is a self-discharge resistance, a series of resistance. Those unknown variables are main factor of battery uncertainty. And even this uncertainty is depending on the temperature, time, and remaining energy. So even the battery is complex. Let's start with the simplest model, modeled by resistor and capacitor. So the battery experiencing IR drop, which is drop of voltage because of the current flowing into the internal resistance. So V loaded is the dropped voltage that you will actually measure. And this, the graph is moved down if the resistance increases. In case of you are using battery more than 100 cycles, you will experience the resistance increases, and also the load current increases, and also the temperature decreases. So by just by measuring this fully loaded voltage does not give you a proper level of energy. So what this makes confused, so usable capacity versus original capacity. So all the label of the battery shows the design capacity, but you are not able to use that energy 100% because of internal resistance. So some of the energy is consumed by battery itself. So you will have slightly under voltage than open circuit voltage, which is a true level of energy based on the open circuit voltage. So you will end up with the actual maximum is less than the chemical maximum based on how you consume the battery. So the resistance curve change over temperature. So this is a graph of the resistance curve based on the temperature. From 0 to 50 degrees Celsius, you will see a pretty large gap between the temperature. So the impedance, which is internal resistance, is strongly dependent on temperature, and also by using the battery more than 100 cycles, you will experience also the change of resistance because of age. So this shows the battery aging. So in a cycle 1, it will show most top graph here, while the cycle 100 shows a slightly less voltage. And also internal resistance changes like 2 times. So this resistance change has to be addressed to measure the proper energy level of the battery. Also, the transient response makes us hard to estimate a battery level. For example, the voltage when the load is on and off, their behavior is different. So when it is on, it has this curve, and when it is off, it has this curve. The most difficult thing is to recover from the load removal to the original open circuit voltage. It takes about 2,000 seconds. So right after the load removal and 3,000 seconds, the voltage difference is somewhat over 20 millivolts, which is quite large. So this also difficult factor of estimating a battery remaining. So like EKF, we need an estimator of battery capacity. Still, how do we know how much percentage of energy left in the battery? So how to estimate a battery capacity? There are one well-established model to measure change in capacity, voltage lookup, and Coulomb counting. This is done in the PX4 too. And the other way that has developed is to develop a cell model, which is modeling a battery in a proper mathematical model and calibrate the model parameter in a proper environment that will give you a better accuracy of battery estimation. So the voltage lookup, you can imagine this. In a glass of water, to measure the amount of water inside the cup, the most easiest way is reading a water level by looking. However, to have a confident in that level, the water has to be stationary. Likewise, to read the voltage to figure out the remaining capacity, the voltage has to be stabilized, which means at least 2,000 second waiting, which is almost an hour, and also the temperature is important. So this ideal situation is never given in when we operate the drone. Also, the open circuit voltage curve is important. For example, the capacitor, also the energy storage, it has open circuit curve like linear here. However, the battery could be regarded like the cocktail cup. So initially it increases voltage very fast, and it has some flat curve here, and then at the last it also increases in a steep. So this is a hard part of reading the open circuit voltage of the battery. So it is not linear. As it is not linear, if you not model this steep curve, will fail to estimate a battery level. Also, the other way is a current integration. So this is somewhat called a power brick in the PX4 pixel. One can also measure how much current goes in and out in a system. In battery, capacity changes can be monitored by tracking amount of electrical charges going in and out. Simply just adding up how much current flowing or draining into the system. But how do you know the amount of charge Q0 already in the battery at the start? For example, when we plug the battery to the to current power brick in the PX4, you will have 100% at the beginning, but that's actually not true. So how do you count charges accurately? Also the problem, because shunt resistor also have a uncertainty over temperature. So our main concern is how much capacity is really available. So to figure out this, we have to figure out this internal resistance in an accurate level. But the problem is internal resistance is different over remaining energy and also the temperature. So what we are really looking for is available capacity here. So the design capacity is basically a label on the battery. So it shows some numbers like 3,800 milliamps. Such number is a design capacity. The full charge capacity is actual amount of energy inside a battery. Sometimes it's over the design capacity, and sometimes it is under the capacity. And what we really interest here is available capacity. How is this known? So you may experience some very uncertain level in the iPhone, for example. Even though it has like 20%, it just suddenly drops to the 1% and goes off. So even this like billion selling consumer level device is failed to estimate this available capacity. So this is also hard in the drone battery too. So there are a few different fuel gauging methods available. First is a cell voltage measurement, which is implemented in the PX4 too. It measures the cell voltage. The advantage is simple. Just by measuring the cell voltage, it shows some idea of remaining energy. However, as I talked about it before, there are many variables that makes this voltage measurement uncertain. So it's not accurate over load conditions. It's accurate when you stay the battery about an hour and measure the voltage. The other way is a Coulomb counting, which is counting actual energy put in and out to the system. It measures and integrates the current over time. However, it is affected by cell impedance, affected by self-discharge too. So to mitigate these issues, there are impedance track algorithm has been proposed by Texas Instruments. So it directly measures the effects of discharge rate, temperature, and age and other factors by learning cell impedance. So cell impedance is the most critical factor of estimating battery capacity. So what is impedance track does? Impedance track keeps the table in a data flash first. So open circuit voltage is kind of very important characteristics of the battery. Regardless of capacity, if a group of battery is using the same electrode, they will have the same open circuit voltage trends. So if we do know the depth of discharge, function of depth of discharge to open circuit voltage, we can estimate the energy level. Vice versa, the depth of discharge can be estimated by open circuit voltage. The depth of discharge means the remaining capacity, for example. And as we know, this resistance here is internal resistance. So it caused the voltage drop over open circuit voltage according to the load. So impedance learning is possible when we know the open circuit voltage. This is actually predictive variable or function of this. And actual measurement of voltage and current will give the impedance value here. So the impedance track represents the tracking of this impedance over time by measuring voltage and current accurately while we have a model of open circuit voltage of a certain battery model. So here also Qmax is updated based on every iteration. So this will help the accurate estimation of the battery. Also, the run periodic simulation of remaining and full capacity by predicting open circuit voltage based on depth of discharge, and this is a function of also the internal resistance. So to measure the resistance, data flash is a data table inside this SoC, contains a fixed table of the function of temperature in SoC, which is output is open circuit voltage. So impedance track algorithm doing real-time measurement and calculation during charge and discharge. So it basically calculates the voltage drop accurately so that the algorithm testing the current table and determine whether that table will be updated or not based on the differences. And also because of the curve, the discharge curve of the battery, as you see, the beginning is very steep and there are some flat region going through, and you will end up with very steep drop of the voltage. So to aid these characteristics, impedance track algorithm checks the impedance every 10% of depth of discharge until the 80%. And then from 80% to until the fully discharged, it has a 3% intervals. So it has a more fine level of the resistance measurement here. So by iterating this, as battery current is consumed, it will update the resistance value like this. So every iteration from depth of discharge 0 means the fully charged, and this is a fully discharged. It updates the table of the resistance. So every single region, the resistance value is changed. So here is the most critical part to estimate the remaining capacity. What is the benefit of this fuel gauging and impedance track? For example, this is one example of if you perform the voltage only shutdown, you will end up with 120 minutes runtime in this given condition. However, if we drain the battery until the 0% based on impedance track algorithm, you will end up with 168 minutes runtime. So basically, you can extract the all energy from the battery based on the accurate information. So the typical smart battery architecture is like this. So here, a discharge and charge MOSFET. So enabling this MOSFET will enable you only charge or only discharge or both enabled. So if you have some undervoltage problem, then the charge MOSFET is open so that no current could be consumed. And also, discharge. And also, when there is an overvoltage problem when doing the charging, this charge MOSFET is closed or open to control the current flow. And this is called the gauge integration circuit. So the gauge integration circuits from beginning to the end of the disposal, it calculates the internal resistance and current consumption all the times, and it outputs the information through the SMBUS, which is standard of this battery system. And there is a chemical fuse. If there is some critical problem happen, then it just blows up the chemical fuse. So these are typical smart battery architecture, and for now the SMBUS is implemented in the PX4. Also, the UAV CAN is implementing. So you can check out the drivers and SMBUS. This is a basic implementation of battery SMBUS on the PX4, and also we developed the PX4 compatible smart battery, which means in SMBUS, and the battery spec is 4800 4S SMBUS, and fully calibrated and tested 90 amp discharge is possible. The nice thing about this smart battery is because it controls the charge and discharge FET, you can just use a simple charger like this. The current is controlled on this charger. The only function required of the charger is controlling the current, so that it should no more than 1 C of a battery capacity. So here is a voltage graph when we use a smart battery. For example, it starts from the 16.8 volt, which is the typical max voltage of the 4S cell, and it sharply drops until 16 volt in 1 minute. And then there is some flat region that's going on, and there is some as it is drained, the curve becomes steep like this. However, measuring and estimating the battery capacity from this voltage graph is somewhat uncertain in this region and that region because it is not linear. If you draw some straight line from here to here, it's a pretty not matched. However, the state of the charge graph is linear, so the impedance track algorithm calculates the state of charge accurately from 100% until the 5%. So it calculates the state of charge linearly so that we can linearize the response of the voltage into the state of charge, which is a percentage based, more informative. So here's the end of presentation, and what I presented here was the battery characteristics and what's the advantage of smart battery. So I'm happy to accept the question. Thank you very much.
Can you hear me?
I can hear you.
Awesome. Thank you for that. Can you stop sharing your screen for a moment? Let's see if we can change your video view.
Sorry?
Just wanted to know if we can change your video instead of your screen share.
Okay. I stopped.
Yeah, no worries. Thank you. I just wanted to thank you. That was really interesting. There's a few questions on chat. Unfortunately, we're running behind schedule. So why don't we do this? Why don't we jump on to the PX4 Slack?
Okay.
There's a PX4 Dev Summit channel. Let's jump on there. Let's try to answer questions from the community, and I'll get back to you on that.
Thank you.
Sounds good. All right. Thank you, Hyun. Oh, nice. Look at this. Hey guys, welcome back to the PX4 Developer Summit. Your host Ramon Rocha here. I'm still here in Tijuana. I'm still streaming to you. We're still live. I can't believe my laptop has survived this far, streaming without nonstop interruptions. This is amazing. Thank you everyone for the response. This is so exciting. Like seeing all those live views right now, it's making this really worth our while. Gotta be honest, like we were planning for this event, and just like last year, we didn't really think we were gonna get so many registrations. It's crazy. Thank you. It just means that this community keeps on growing and that this industry is going really big. Next up, we got a really interesting conversation with Chili Food. Do you guys know who this guy is? I'm gonna give you a quick look at this. I just got this dropped by the mail this week. So next up we got what's the difference between a drone and a flying robot by Tuli Food. He's joining us from San Francisco, California. He's the Community and Business Development Manager for Open Robotics. I'm really excited to have him here. He's also a repeat speaker from last year. Make sure you guys are joining us on Slack. Community volunteers, please do me a favor, post the link.